Welcome everyone. In this video I would like to test some Peltier cooling again. I got some new stuff and I also made some modifications to some of my older things, and I want to show them to you so we can learn these things together. So as you can see, we have a few fans here, an Arduino circuit, an 8 ampere unit. So here I will use the 8 ampere unit, so TEC 12708. And this is our old friend, this CPU cooler. And now, as you can see, I have removed the fan, which was this guy here. It's a very weak fan, so 12 volts and 0.17 amperes. So yeah, it's as it is written here, 0.2 watts. So it's not a big performance. So now I got this, and actually this is an Antminer fan. I bought this based on some of your recommendations, so thank you for that. So what you can see here, this is a very well balanced fan. It has a nice bearing inside it. I think it's some sort of fluid based bearing. And then this takes up 1.85 amperes. Actually, I tested it and it runs at 2.2 amperes at 12 volts. So it has even higher performance than it's described here. And it has 4 wires. So if we start from this side where there is a number 1 on the connector. So we have GND 12 volt connection. And then we have the output of the signal of the RPM value. So there is I believe a magnetic sensor inside the body of the fan, and the magnetic sensor of course gives a periodic signal that you can measure on the 3rd pin from this side. So you measure that thing and you can get the RPM value of the fan. But there's a 4th wire, and I will use that with this circuit. This is the PWM controlling wire. So you can have something which can generate a PWM value. I will use an Arduino in this case, and you can modify the RPM of the fan between certain limits. And just a comment, these fans have a different standard. So the Arduino by itself runs at 490 Hertz or something like that when it is providing the PWM signal, but these guys require something between 21 to 28 kilohertz, so much higher frequency. So you have to do some small modifications on your Arduino in order to be able to provide a 21 kilohertz PWM signal. In fact, I will provide 25 kilohertz, that's like the middle. But there are libraries and tutorials available for that, so I will not bother about it. I just tell you that you know about this thing, because if you notice that you cannot directly drive your fan with your Arduino, then it might happen that you just provide the wrong signal. So I removed the fan from here, but obviously this is a too big fan because the previous one was 8 centimeters. And as you can see, this covers the entire area. So what I will do, I just put it here. I will use some wires or something and just attach to it. And then I made another modification to this. So we have now our fan, and I discussed it. So you can see 2 holes. The first hole is a failed attempt. I used my hand drill and tried to drill a hole through this aluminum part, so I can insert a thermometer, a K-type thermocouple, into this hole, so I can measure the, let's call it, hot side temperature better. So I can measure this temperature which is attached to the hot side of the Peltier unit, like this. And then if I'm here inside this block, then I have a better information about the real temperature of this thing. But then that was a failed attempt because I broke the drill into the hole. Of course, It was a very small drill bit, and also a very bad decision to use a hand drill. And then finally I bought a proper, not proper, but at least some more useful column drill. So you see the second hole, it's a bit off-centered, but still it goes quite deep. I might be able to show it. So this is a piece of wire, and then yeah, so now this is in. So roughly, let's say 4 centimeters or 3 centimeters, and that's almost the middle, because it's the hole starts a bit, you see this edge here. So if I put it there, so roughly here we will have the thermometer above the copper tubes. So of course I was careful enough to not drill into the heat pipes. We will see. So this is the other modification, and what I will try to do here is I will try to change the cooling by using this fan, and then see what kind of cold temperatures can we achieve on the cold side of this. And again, I have to emphasize this, that the system will be something like this. I will use a clamping mechanism, of course, to keep the thing on the surface of the heatsink, and this will provide a somewhat firm contact. And of course I cover the top and I put the thermometer right on top of this thing, but there will be no other things attached to the top side of this. So the heat which is pumped from the cold side to the hot side by this Peltier unit is very low, which means that the DT value, so the temperature difference between the cold side and the hot side of the Peltier unit, is relatively high. So that means that we will see very low numbers. I expect -23, -25 degrees, because I already did some similar experiments previously. But you have to notice that regardless the low numbers, this is not a good cooler if we are able to reach, with this very setup that you see here, if we are able to see -20 degrees Celsius. So you don't even think about making this into an air conditioner or something, because just see how small is this unit. So no, that will not work. I just want to demonstrate that we can have a bit better control over the temperatures, and how we can use this to cool something which we can cool within a reasonable domain or reasonable area. So let me prepare everything here, and then we will see what we can do with this kind of setup. So I almost finished assembling the system, but I just want to show you how powerful this fan is, or how loud it is. So now I minimized the PWM control. Actually, it doesn't work in the same way I want it to work, but let us see what happens. So I just try to grab the fan. So now you can hear it, at least, but this is like a very minimum RPM. And now I crank up the current. So in this condition, 0.2 amperes is the current which is running through the device. So I go to, I don't know, 0.5. So this is roughly 0.5 amps. This is 1 amp. Two amps. And this is very, very, very powerful. Okay. And this is the maximum, but it's crazy strong. So my idea is to start with this very low setting and see what is the minimum temperature here on the top of the Peltier cooler. So I will have the system like this, and I use these rubber bands to sort of attach to this in some way. I don't know yet how, but I will solve it. So this is now clamped down, and it's strongly fixed to the surface of the heatsink. This is the cold side. I will also cover this by a plexiglass or something like that to hinder any kind of thermal interaction. And I will use this thing again. So this is my Peltier power meter. So here we will be able to see the current, the voltage and everything, but I will not use this to log the values. I don't want that, I just want to see it on the screen. So I continue assembling this thing and I come back to you after I finished everything. So everything is hooked up and I hopefully haven't made any mistakes. So what you can see, this is the power meter part. I will use another meter to measure the current running through the wires and also the voltage, just to make sure that we get the same readings. But the purpose of this test is not the measurement of these values. And here I used a piece of foam that you can see through this small window, which is pushing down the K-type thermocouple against the cold side. So that should make sure that the contact is nice. And there is another wire running inside that hole that I showed you. So that should show us the hot side temperature. And I have the PWM regulator or controller, and I have the 6500 RPM fan here, and 12 centimeters, so it covers the whole area of, or entire area of the heatsink. So we will see. And first what I do, I just turn on the fan, and then that will be noisy, so I won't be talking too much. And then I turn on the power supply, so this guy here, and go to, let's say, 5 amps and see what happens with the lowest setting that I can set with the PWM. And then I will show you that if I change the cooling, but I still keep the power supply at 5 amperes, then the cold side temperature will change. And that is because we changed the hot side temperature with the increased cooling, and that shifts everything on the curve. And based on the values that I measure here at, let's say, a few different values, 5, 6, 7, 8 something amperes, I will try to calculate the things based on the performance chart, and we will see how they agree with each other. I mean, the measurements and the performance chart values. So let's turn on the fan now. So this should be a bit louder. So in the beginning it revs up, but then it stops at a certain value. And now it is 0.2 amperes, 0.25 amperes is the current consumption of the fan. So now you can see that 25 degrees is the temperature on both sides. So that's pretty good. And I just start the power supply of the Peltier unit. And I set 5 amps, so I go until 5 amps. So this is 5 amps. This is saying 5.1, that's very nice, and the voltage is 12.2 volts, which seem to be a bit off, because 13.2 can be measured on the power supply. So let's see what causes the discrepancy. So you should be able to read the voltage, hopefully. Yeah, 12.3 on the output of these things. So there is a voltage drop, probably caused by the device. .6 on both sides. Yeah, the voltage drop is caused by the cable that I put here, and I actually found that out in my last video, but now I can confirm that that's the case. So that's just, I guess, due to the poor contacts and stuff like that, but it doesn't interfere with our measurements. And it's 5 amperes, that's more important for us. But 5 amps and 12.5 volts, that's what we know. And the temperature is minus 19 point something degrees Celsius, so that's pretty nice. So I think I go up to 6 amperes, because this is the 8 ampere unit. And the temperature went down to minus 20 degrees, and the hot side temperature is 32.2. Of course, I should let this run to get the temperatures to equalize. What I can see here is that I was running out of digits here, or available spots, so I replace the thermometer. Minus 24. That's quite nice. And let's see what is the hot side. .8. That was pretty much the same. So that means that actually we are very close to the room temperature. So here we see 33 point something. So that's not our problem. So it seems like we are cooling this thing very nicely. I can feel that the heatsink is like gently warmer than the room temperature. So we could see what happens if I increase the cooling, whether we get better temperatures on the cold side. So I can see that the temperature drops. But seems like that the Peltier unit doesn't want to change, so I increase the current to 7 amps. And now you see that the temperature increased on the cold side. So I increase the cooling. Seems like this is the maximum. Now I go down to 5.3 and see what happens. So it is 21 degrees, minus 21, and 29.5 or 29.4 on the hot side. That's pretty close to the room temperature. So if I was using a different Peltier cooler here, I would be able to still maintain better cooling power because of this fan. Minus 21. This is the heat sink or the heat pipe temperature. And of course here there is a hole. So I did not entirely isolated everything properly, so that might be some of the problem that we don't go below minus 21. But it's already a nice performance. So 29.5 here, and let's see what happens if I almost eliminate all the cooling. So now it's just a gentle breeze, and you can see that the temperature went up immediately. So 30.3. And I have another idea to try, so let me see if I can do that. So we can see that the temperature went up by 2 degrees. So what I try with the hot side, because now it seems to be stabilized, I will use this sprinkler and sprinkle a small water on the fins of the heatsink. But before doing this, I want to tell you that you should not do this, and I should not do this either, but you should not do this because water and electricity are not good friends, especially when you are potentially can be involved in the circuit. So don't do this, but I'm a semi-professional, so I can do this. So let me just sprinkle. I will try to sprinkle some water in between the fins and try to put some water on both, and we will see what happens with the numbers. So now we have to wait for the magic, if there is any magic happening. And it is happening. So look at these numbers. It's decreasing. And now I crank up the RPM. It will be noisier a bit. So, we almost went back to the same temperature without significantly increasing the RPM of the fan. So, let me put some more water on the fins of the heatsink and increase the power of the fan to the max. So what can be potentially interesting here is that by using this sprinkler, I was able to decrease the temperature on the fans of the heatsink. And this is because of the evaporation of the water molecules or water droplets on the fins of the heatsink. So when I sprinkled this thing on it, of course the droplets are quite small, so they have relatively large surface area, and then due to that they could evaporate easier if they have larger surface area. And also I was blowing rapidly moving air on them, so that was also helping this process. So as you could see that the temperature dropped to 27 degrees Celsius on the back side of this, and now it's like 6 degrees higher. Of course I removed the high RPM of the fan, but still. So why that is happening is because the evaporation removes the heat from that area where it is happening, or something like that. So that heat removal is cooling, as I explained it in some previous videos. So we help the cooling by introducing an extra step of cooling. And as we know, the cooling or heating is more different when there is a phase transformation involved. So in this case we had the liquid to gas sort of transition, and because of this we could remove an extra amount of heat from the system. And in the freezing process we experienced the opposite of this. So when we wanted to cool down the water's temperature below 0 degrees Celsius, first we had to freeze it, and we had to pump out the latent heat as well from the system before being able to cool down below 0 degrees. So as long as we had the liquid and solid ice phase in the same volume, then the temperature was stuck at 0. So when we go from liquid to gas, we gain some sort of extra energy, if we can phrase it like that. And it's not cheating at all or something like that, so this is still physics. It's just like you are sweating in the hot summer days, and when the fan is blowing the air at you while you are sweating, you feel that the air is very cold, and that is nothing else, just evaporation. So here we could do the same, and by that I could maintain the same minus 20 degrees temperature on the cold side, but I was able to go up from 5.5 or 5 amperes up to 7 amperes. So that means that we were able to maintain roughly the same DT value, but since we increased the current, we increased the DT as well, so we stepped up on those lines. So for example, if you want to have a better cooling for your hot side of the Peltier cooler, so it's not necessarily for reaching lower temperatures, but being able to provide more current to the Peltier, then you should consider this. But I think there is a safer way to do this, and in the next video I will do that and show you how to do it. I'm actually waiting for some more parts so I can put together some better system, and I will ditch these electronics or put them into a box, so I don't have to worry about the electricity and water combination, or I don't have to care about it that much. So I will do that and show it to you, because this can be something which can help you to reach better cooling for your Peltier cooler, and you don't really need anything else than just some extra water. So I will show you how to do that. So I hope that this video was useful and it was entertaining. I just wanted to show that I basically have this new device, this fan, and it's a very powerful fan, and I can just change the RPM of it by playing around with the PWM controlling with the Arduino. And you could see that we can do some serious stuff with this kind of cooler if we provide a very good cooling. So yeah, so I hope that this video was useful and you learned something, and see you in the next video.